It's my pleasure to be here today, sharing some of the research that our team is doing in the UCL Hawks Center, which formerly was Vice Center, and also in the Surgical Robot Vision group. I am one of the assistant professor in robotics and AI. And before I really jump into the topic of my presentation, let me tell you give you an overview of about our team. Uh, we are we are the Hawk Center Institute, which was formerly the uh, Vice and CIMIC Center. So there has been a recent merger with that, and we're based in very close to King Cross, the center of London, um, where we have engineers, scientists, clinicians working together hand in hand for bringing novel surgical technologies into clinical practices. I am also part of the new UCL facility in the Olympic Park. Also, if you are familiar with London and its surrounds, we are based in the Olympic Park area, just next to the Stratford Westfield, where we have built a new robotics facility where we are having various different disciplines of robotics, including surgical robotics. So I'm part of that new initiative in computer science as well. Um, if you happen to be in the area, you can drop me a message to have a look of our new campus around. Then I am part of the surgical robot vision group. Broadly, we are academics in that group. The group is led by Professor Dan Sternoff. We are covering various different surgical procedures for computer-assisted intervention and surgical AI side, ranging from neurosurgery to fetoscopy, ophthalmology-related procedures, general surgery, GI, so on. Also, we look into medical imaging side of various different procedures as well for computer-assisted diagnosis, and also different kind of imaging technology. So one of the area that we are working on is multispectral or hyperspectral imaging, or building new devices for surgical interventions that can give a better visualization during the surgery through enhanced imaging, that is hyperspectral imaging. Then part of our team, led by Agostino Stili, he is really the lead of surgical robotics or soft robotics in our team, where we are building new novel robotics instruments or soft robotics intervention technologies for various different range of surgical procedures. I'm sure most of you are from robotics backgrounds. I really don't have to motivate too much, but I'm not sure how many of you are from medical robotics side. Okay, many of you. Okay. So let me start by giving you an introduction on what is missing in the surgical robotics, let's say, avenue. So we have surgical data science, a lot of algorithms getting developed with the digitization of the data. We're getting a lot of data from clinical practices where we can train our model, make them quite robust in terms of precision and so on. But then we have another stream where we are building novel new surgical devices. Again, currently, most of them are in their design and development phase, where we have very less interaction between the two, like design robotics for surgery or for medical robotics, and then AI. So where my research falls in is bringing AI into surgical robotics or surgical intervention for making them highly precise and making surgery highly precise and safer. If we talk about robot perception in general, so self-driving cars are there, almost moving towards autonomy, where we have multitude of sensors, which include cameras, LiDAR, sonar, stereo, RGB, D, IMU, you name it, and those array of sensors are there. Yet we are moving towards autonomy in these systems, not yet that we managed to make these systems autonomous. Having said that, we are somewhere between partial autonomy in most cases to some prototypes are now like towards autonomy. But when we talk about perception in surgical robotics, we have to rely on very limited sensors. Vision is our main source of sensors, and in some cases, we have kinematics data available. But those are the main sensing streams in current surgical practices that are available to us. Of course, this is due to ethics as well on for new devices and bringing into new sensing kind of technologies into surgery. And then, so we are kind of limited in that space. And then when we talk about autonomy in these procedures, we are really uh, somewhere having robot assistants or surgical assistants where we kind of provide some form of overlays or some displays that can help or guide the surgeons during the procedure, but we are nowhere towards getting autonomy in surgical robotics. Having said that, that's not our goal as well. So we want the surgeons to have full control in the surgery because there is a lot of responsibility involved. Plus, they are the experts in their field. But if we can guide them or assist them during the procedure, which can lower the risk of any post-operative complications, that's our target. Uh, Talking about AI in surgery, so there are more than 231 million open surgeries or major surgeries happening in the world, and then about 13 million laparoscopic procedures. So laparoscopic or minimally invasive procedures, they have a lot of advantages over open surgery, where they provide shorter duration of hospital stay, less trauma, less pain, less blood loss, smaller scars. But they come with limitations and a lot of workload or cognitive load on the surgeons because uh, these procedures, they require high skill level. Uh, the field of view is really limited because the surgeon has to operate in a constrained environment. There is increase again surgeon cognitive load, and then there is no direct preoperative imaging overlays currently in most of the surgeries that can assist the surgeons during the procedure. What our vision is that we can bring guidance or autonomy, a partial autonomy into surgery where we can provide intraoperative support, we can reduce the risk of complication, the trainees, so we can provide some way of improving trainee curves through some surgical simulator systems. We can reduce surgeon cognitive load. So here I'm just showing some examples of where we can display some critical anatomies during the surgery, or having some task perform more autonomously during surgical using surgical robots. Where the research for my team lies in. So I broadly cover two topics. One is context awareness in surgery, where we cover surgical workflow, action recognition kind of stuff, then disease diagnosis and characterization, um, real-time AI assistance for decision support during the surgery. But then the second major stream that my team covers is on reconstruction and navigation, where we have been working in the area of mosaicing or field of view expansion for a few years now, then 3D reconstruction, novel view rendering, then detection and visual surveying um, uh, from the reconstruction. So today I'll cover some of the streams of my team in this talk, and yeah, and I hope I can give you a good overview of what we work on and excite you on the various avenues that we have, open avenues for research in surgical robotics and AI. So the first topic I want to cover is on reconstruction in endoluminal procedures, where computer-assisted imaging-based task in endoscopy has a lot of potential where we can do landmark recognition, but it requires human-level annotations. Most of these tasks requires annotations from human annotators. Then we can do polyp detection, tumor characterization or polyp characterization, or performing some therapeutic treatment. Uh, for these kind of tasks, still expensive, but annotations can be obtained. But when we talk about reconstruction in these environment, and especially in intervention procedures, we don't have the ground truth available. So how can we then develop systems that can do 3D reconstruction in these scenes, and then we can also validate that. For that, we've been looking into certain approaches. We're looking at the real endoscopic procedures. First thing that this was the work from our student a couple of years back. First thing that we looked into was classical feature-based methods, how well they perform on, let's say, colonoscopic data. They fail terribly. So how can we really move forward with this problem for camera pose estimation or depth estimation for reconstruction in 3D? So a couple of years back, she worked on building learnable methods for 3D reconstruction, where she looked into designing, like coming up with simulations, Unity simulations for endoscopic environment, doing depth estimation, camera pose localization using these simulations, and then going from sim to real, so domain adaptation for 3D reconstruction in these environments. So her work was quite promising, and it also led to us running a challenge in Mechanic 2 years back, releasing our synthetic data and part of the real data as well, where we released the Colmap as pseudo ground truth for registration. This was covered within one of the project in our team, European project called Endomapper. And then again, this year we are running another challenge. Our team is running another challenge, more or less on similar data in Mikai. So if you happen to be in Mikai this year, so it's on the last day of Mikai conference, so you can pop into Endoviz challenges on that day. Now, as I mentioned, feature matching or finding robust features is a major problem in surgery. But when we pick up the literature from computer vision, it's an open problem also in computer vision literature. And this is to tie up with in-domain data and out-of-domain data. So there have been a lot of methods, recent methods, learnable features, feature-based methods that came in computer vision literature in the last couple of years. But then there is no benchmark that can validate those data sets or those methods, saying which one is the best and which one can support, let's say, out-of-domain generalization. So in this recent work, some of our PhD students, they looked into validating 20 recent from computer vision literature as part of the CVPR image matching challenge. And then they again compared 20 state-of-the-art methods. They showed their performance on out-of-domain data set. So trained on this Nantic data set, but tested also or validated on the other data sets to help us understand where these methods they break and which ones are the top performing methods. This actually, so again, trained on computer vision data sets, but that gives us very significant information for surgical data sets as well. So this is the work that we are presenting next week in one of the ECCV workshop. Taking this further, so some of these methods which were the best performing one, like a light glue or GIM, we then moved on with one of the robotic system for multi-view image acquisition and 3D reconstruction that we have been developing in our lab, where we have acquired from monocular camera, monocular endoscope, we have acquired various samples and 3 different trajectories for various ex vivo tissues, and then using and including getting ground truth from a laser scanner, then using the top performing methods from CVPR, from computer vision, using those methods for then doing feature matching, which is much more robust compared to the classical feature matching, to then use it for using structure from motion, to then use it for 3D reconstruction, and then using the laser scanner as the ground truth in this case. Again, this gave us very reliable results, and this gave us also a system where like data generation in surgery or is a big issue. So this system basically gives an indication that you can have data generated with ground truth that can be used for 3D reconstruction. So moving forward, a little bit about, let's say, nerve or nerve-related research that we've been doing. This was one of the work that we presented last year in McKay, where we looked into like given an endoscopic video data with non-camera parameters and depth information. We trained nerve using also the color information, but also depth information and also the light source location information to then um, have novel view renders or novel trajectories rendered that then can be used for data generation for training deep learning algorithms in this space. Here I'm showing, so two main contributions over nerve that we had in this work was basically conditioning nerve based on the light source location, and then also optimizing the network with sparse depth. So these are some of the results from these methods where compared to nerve, because of having sparse depth incorporated in the loss function, we managed to get much more reliable reconstructions in an endoscopic environment. Then moving forward, this is one of the work that we are presenting in McKay in 2 weeks' time, which is based on Gaussian splatting, which is kind of taking over nerves now because it provides much more real-time performance and much more robust performance in computer vision literature. But it tends to fail when it comes to surgical data because of the texture. We don't have much texture in, let's say, surgical data. So what we did in this work was that again we proposed an end-to-end system. Most of the work in this domain, they start from somewhere like non-camera pose and depth, and then they move on to, let's say, doing novel view rendering. But we treated it as end-to-end problem where we did use an existing network called RNN SLAM for first doing camera pose estimation and depth estimation, mesh generation, doing the point cloud, and then incorporating two innovative loss functions, which is geometric loss and depth loss, where with geometric loss, we kind of force the Gaussians to align themselves to the surface of the tissue, let's say, or the 3D space. As a result of that, we managed to basically get much more realistic 3D renders. And here I'm showing comparison of Gaussian pancakes with the classical Gaussian splatting. Same comparing the normal GS with Gaussian splatting, and then again GS pancakes. We can see there are much more less artifacts generated in the Gaussian splatting case. This gives us 100 times faster performance, so real-time performance compared to nerve. Also, the training time was significantly reduced. So, but of course, the drawback in this system was RNN SLAM again is a couple of years old. It doesn't really work all the time. But having said that, now that we have analyzed the recent computer vision detectors or detector-free matching algorithms, we are hopeful that we can replace the RNN SLAM part with some of the most recent literature to make it actually work more robustly end-to-end. So where we are in terms of endoscopic literature, or what will be the next steps, again, the main highlights are that if computer-assisted intervention can help us improve lesion detection or reducing blind spots in colonoscopy, let's say. It can improve in navigation and mapping, but we are still limited by the data and the dynamics of the environment. So currently, most of the work that we have been looking at is looking at more static scenes or not modeling the deformation nature of the human tissues. This is something that we need to look into before we really want to say that these algorithms can be translated into clinical practices. We are still limited by data availability. In this case, uh, generalization across data from different surgeons or different kind of imaging devices and so on, and then clinical validation or adaptation. Moving on to the next topic, which I'll kind of briefly cover, is context understanding in for AI-assisted decision support in surgery, where mostly we are looking into various different aspects, including steps and face recognition, instrument segmentation, action recognition, tissue instrument interaction, steps and instrument forecasting, and so on. But actually, all of this is interlinked in some way. So when we look at a surgical video, let's say, it's um, it's like a recipe. So the recipe can, at high level, be broken down into phases and steps. It's like, again, when we are cooking pasta, we know what are the different steps in cooking pasta, let's say. Then some parts of the surgery are much more critical when we are around critical anatomies, which require fine-grained understanding of the surgery to then define, let's say, surgeon skills as well in that space, or have systems that can assist the surgeon in those particular phases, which are much more challenging and requires much more expertise. This can have direct, so that will involve um, tissue instrument interaction, detection, and also kind of critical structures identification. All of this can be then tied to post-operative complication uh, or post-operative outcomes. So starting from high level, we are trying to converge to low levels, but mainly in the most critical part of the surgery. We have been looking into various different types of surgery, but more commonly, we are looking into pituitary surgery, um, which we started off with having a high level understanding of steps and phases. Before jumping into that, what is pituitary surgery? I don't know how many of you know what is. Uh, yeah, okay. So pituitary is a small pea-sized gland which is really located at the base of the brain. It's considered as part of the brain, but in order to treat tumor in that gland, instead of going through the brain, which will be much more damaging, surgeons perform this procedure through nose. So it's an endonasal procedure where they open up the space. These are the different steps involved, reach to the tumor site. But once they are at the tumor site, they are really looking at a lot of critical structures, including optic nerves, carotid arteries, and any damage to that can lead towards adverse outcome or long-term blindness and so on. So in helping or supporting surgeons in this type of surgery, and also um, for building their training systems, we have been looking into this surgery where first, again, we looked into steps and phase recognition. Then within certain part of the surgery, we looked into critical structures, segmentation, and landmark-based identification of where the optic nerves are. This was one of the preliminary work, which we then further, uh, the results were good, but not as good as it can be used in the clinical practices. So we then moved on to further improving this network and also doing some clinical validation. Uh, uh, so with the improved network, we managed to get much more reliable segments and much more reliable landmarks like optic nerves and stuff um, in this procedure. And then we are further working on translating this system into NVIDIA embedded devices, which can be taken into operating rooms. Within this space, we have been working on building. Uh, this is the work we are presenting in Mikhail again. We've been looking into a skill assessment for surgery where we have trainee system which is shown over here, and I'll show it in the next slide as well. So for fetus, neurosurgery or pituitary surgery, these are the kind of system they use for training the new surgeons, let's say trainee surgeons, which is a high fidelity phantom. Again, it gives the same different structures or different phases and steps as of real surgery. But when these training sessions are getting performed, the expert needs to stand next to the trainee and narrate them that what is happening and how they should approach and so on. So really guide them on how they perform the procedure. In one of our recent work, we looked into using instrument tracking and some of the parameters with instrument tracking, then detecting the surgeon skill level. So if it's a trainee surgeon or an expert performing the first step of the procedure or first phase of the procedure. Then using those methods that we use for instrument tracking for this work, we into this NVIDIA hardware for then providing real-time guidance in terms of the instrument or where the instrument is, so instrument position, and then taking this work further, we are trying to integrate anatomy detection or landmark detection into the same system, but real to sim, there is a huge gap because we managed to do landmark detection in real surgery, but when we want to go from that real surgery to sim, it doesn't always work, especially for anatomy. For instruments, these are the same instruments, so there is not much problem with that. So here I'm going to show you some of the videos from our current, let's say, trainee setup, where we have this AGX device from NVIDIA, and then the pituitary phantom, which actually has the same nasal cavity as of a human, and then we've been doing instrument segmentation and tracking and various different kind of AI interfaces for pituitary surgery. The idea for this is that if we can build a trainee system that can provide guidance in terms of instrument, guidance in terms of anatomy or where the critical anatomies are, and let's say distance to critical anatomy, and create some form of alert. That's our first goal, and that's a low risk goal, because we are not saying we are actually taking this into surgery. This into surgery will take several years. Within this same stream, one of the topic that came in discussion was basically time to surgery. So operating or managing operation workflow is quite important. Like, when do certain instruments need to be handed, or when do anesthetics have to take certain actions? So taking this idea provided by our clinicians, we started to look into time to surgery or remaining time to surgery. So again, this is the initial part of this work is based on the step recognition and then building networks on top of that. We managed to get promising results for that, but since our step recognition work is not so mature, because the current literature in McKay community or surgical data science community really is overfitted to some certain data sets for step or phase recognition. But these algorithms, when you go outside those data sets, they don't tend to work very well. So there is a lot that needs to be done in the space of pituitary surgery or workflow analysis or step recognition in pituitary surgery to then take it further to fine grain level. So we got promising results, especially towards the end of the surgery, but we still need to work a little bit more on this topic. Uh, we have some of our data uh, is released publicly a couple of years back because we organized a challenge 2 years back in Mackay on pituitary workflow recognition. So I don't really have a slide for that, but if you are interested in this problem, you can look for this work on our center website. Uh, Another interesting topic that we've been looking at is LLMs for visual Q&A in pituitary surgery. So again, taking the same data set of about 25 videos from which are now in public domain, um, creating another layer of data set for Q&A where we have 15 steps, 4 phases, 18 instruments, uh, three quality of instruments exist, and then 5 positions of instrument, whether the instrument is in top right, top left, and so on, and then operation notes. Using this information, uh, uh, some of our students, they looked into creating like image text embedding, and then using chat GPT-2 backbone, and then basically given a question, predicting what the response should be. And this for this we compared it with the various different existing LLM based method, including surgical GPT, and managed to get better performance. And this is an oral in Mackay. I believe it's on the third day of Mackay. So yeah, what's our vision for neurosurgery or endonasal surgery? Uh, that's like the high level picture where we have, uh, in fact, this kind of translates to any kind of surgical procedure or most of the surgical procedure where we have massive information available in terms of preoperative data, preoperative planning, intraoperative data, and then postoperative data, which is also postoperative like outcomes, including any kind of biochemical profile, clinical notes, and so on. So if you have this magnitude of data set, you want to basically we want to do workflow analysis. We want to go fine grain in instrument detection, fine grain in interaction detection, critical structure detection. And if we can understand the surgeon action, so instrument tissue interaction and how the trajectories are being followed, uh, we can basically correlate it with also with surgical outcomes, and can also provide real-time guidance in some way of telling them to recalibrate their trajectory and so on. So that's the overall vision for the project. Uh, I would say we are pretty much halfway through, but a long way to go as well, especially when it comes to real-time, the actual intraoperative procedures. Um, Yes, and then in this work we are doing also in collaboration and support from NVIDIA and Medtronic, where NVIDIA has been kind enough to provide us some of their embedded devices for translating some of our algorithms. Uh, we have been heavily involved in outreach activity for this work as well, where we managed to get our work displayed to some of the leaders in robotics community, managed to create some news headlines as well, also in BBC and so on, last year. And having said that, actually, this brings me to the end of my presentation. Um, I would like to thank our entire team, Surgical Robot Vision team. This work couldn't have been possible because without their support. So thank you so much for having me here today.